Question number 6 of JEE Main 2016. A satellite is revolving in a circular orbit at a height h from the Earth's surface. Radius of Earth is r, and r is much greater than h. The minimum increase in its orbital velocity required so that the satellite could escape from the Earth's gravitational field is close to neglect effect of atmosphere. Let's go over a little bit of theory. Orbital velocity is the velocity required by satellite to revolve around the planet in a circular path. And since the satellite is revolving in a circular manner, the force that it will experience is the centripetal force, and centripetal force is given by the formula mv square upon r. Let's see what centripetal force is. Let's say there's a ball attached to a string and you're making the ball go round by pulling on the string and revolving it. So the ball will experience a force which will push it towards the center. If this force is too much, the ball will hit you. If you let it go off, the ball will fly off in another direction like this, and that's why centripetal force is also called center seeking force. So we also know that force is equal to the gravitational force is given by the formula capital G times mass of Earth times mass of object, in this case satellite, upon radius square, which is the radius of Earth. So if the satellite is moving in a circular fashion, these two forces have to be equal. There are two different formulas for the same force. One is in terms of V and another is in terms of mass and gravitational constant. So if we equate these two, we'll get mv naught square upon r plus h is equal to g mm upon r plus h whole square, which comes to v naught is equal to, if you equate it, square root of gm upon r plus h. So h can be ignored because it's given in the question is too small and won't make much difference in the calculation. So v orbital is equal to square root of gm upon r. Now we want to get rid of capital G and we want everything to be in small g in terms of acceleration due to gravity. So what we can do is again use this formula right here. Force is equal to g mm upon r square. We know that force is mass times acceleration. So mass times acceleration due to gravity, because the satellite is accelerating at the rate of g, and which is equal to g mm upon r square. So m will cancel out and capital G will be equal to g r square upon mass of Earth. So if we substitute this value in this equation, you will get square root of g times r, right? So you can work that out. And what is the escape velocity? Escape velocity is the minimum velocity that an object requires to escape the Earth's gravitational field, right? So v escape can be calculated using the formula for kinetic energy, because the object will have to have certain kinetic energy. So here if you see, half mv square is equal to g mm upon r square. Mass and mass will cancel out and you'll get v square should be greater than 2gr. Again we substituted capital G equal to g square upon m. So if you substitute this value here, you will get v square is equal to, v square should be greater than 2gr, or v should be greater than square root of 2gr. So v escape is approximately equal to square root of 2gr. So now the question asks us to calculate the extra velocity that the satellite requires to escape the Earth's gravitational field. So extra velocity required is v escape minus v orbital, which it already has. So we just calculated v escape as square root of 2gr minus square root of gr, which is the v orbital, and we can take square root of gr common from this expression. So square root of gr multiplied by root 2 minus 1. And the question is the minimum increase it requires so that it could escape from the Earth's gravitational field is close to option number 4. So if you liked my video, please click on the like button, comment and share, and also subscribe to my channel. Thank you very much for watching. And introduce small g, which is the acceleration due to gravity, and the way we do it is by using this expression again. So instead of